So, again welcome to you all for the third lecture series of the course Perception Algorithms for Automations or Autonomous Systems. In last lecture, we have completed primarily the introduction part. So, what is an autonomous system? What are the different functional layers of the autonomous systems? We talk about the software stack of autonomous systems when the sensor data is coming, the perception stack, the planning stack and the control and actuation stack. Also, we talked a bit about the navigation stack. So, the details were covered. Two examples were practical examples, actually industrial examples were cited. One was with the advanced driver assistance system, another one is a UAV based maritime surveillance systems or reconnaissance systems. So, with this we have shown the integrated SPA, sense plan act loop, as well as the OODA loop for the military application. OODA means observe, orient, decision, act, all this loop. So, next we focused primarily on the perception system, as this is our course, this is what we will be learning. So, perception system we already told is already divided into three categories. One is the detection, processing and tracking, then the classification and the multi-sensor data fusion. So, what we will be we started some examples of we started first tracking with some examples of primarily reviewing or brushing up the courses on estimation theory. So, we started with least square estimation. We discussed what is the generalized list, what is the least square for a first order time domain signal. So, when it is a first order signal, that means it is only position and velocity. So, we are discussing the first order fits. So, first order fit, as we discussed yesterday, that it is primarily the position and velocity fit. So, it is a kind of linear fit. So, you have two coefficients A0 and A1, the position coefficient is A0, velocity coefficient is A1, and what we did a least square estimation with the measurement minus predicted the square of that, the error square, and we took that is our cost function and we solve for A0 and A1 by solving an optimization problem. So, here is the optimization. So, we discussed about this in the last class. Today's class we will be starting with the second order fit. So, what is the second order fit? Obviously, just an extension of a first order fit. In a first order fit, you have only position and velocity. Now, we will take a acceleration component also. So, you can see this, it is a kind of a parabolic fit. So, from a straight line, now I am going to a parabola. So, with this you have your A0, A1, A2, the three coefficient. Methods are same, your measured minus predicted, square of that error should be is your cost function and you need to optimize it. So, you need to derive your coefficient by minimizing the error. So, del j by del A0, del j by del A1 and del j by del A2. This has to be 0 and you have to solve the three simultaneous linear equations. Once you solve this three simultaneous linear equation, you get this is your output. Okay. So, methods are same and it is just an algebraic equation. When I say k runs from 1 to n, is as it is known that it is the number of data points that are there here, and yeah, so the number of data points you would like to fit it into a second order polynomial. Okay. So, once the quadratic curve is done, then we will go for a third order fit. So, third order fit means what is the third order variable? So, first order is actually or say 0th order is a constant signal. First order is a position velocity model. So, it is a uniform velocity model. Second order is a constant acceleration model. So, what is the third order? Third order is called a constant jerk model. What is called jerk? Jerk means rate of change of acceleration. So, meter per second cube kind of thing. So, you have, so it is a variable acceleration model or a constant jerk model. So, you have seen it is kind of a cubic polynomial. So, A0, A1, A2, A3, you have 4 coefficients and obviously your matrix size is going to increase because you are going for a higher order fits and all. So, you can see it is a 4 cross 4 your coefficient matrix and this is your the other vector. Okay. So, with this you can get a third order fit. Now, as you increase the order, depending on your data points, what kind of data you have, you can get a fit. Now, how will you know which is my correct or which is not? So, I just wanted to give you some examples. So, suppose now in simulation, you know I am simulating suppose a quadratic signal, say a parabolic signal, say 5 t square minus 2 t plus 2 is equal to x. So, you have your position component as first derivative of this and the velocity component is this. Okay. So, you got something like this. So, this is your actual curve, the dotted line as you see, the dotted line is your actual curve. Now, with this first I would like to do with a first order fit and then I would like to do a second order fit. So, I did a first order fit. So, this is a quadratic signal, but I wanted to do a linear fit, simple linear fit. With this linear fit, what we got? So, we got say this is your estimate. Obviously, this is more error and this is say data point. So, if this is the data points and this is your say the actual fit of the signal, well it is passing through the data point, but not a very good. And if you check the error, you can see the error here, your error in x and error in x derivative. Okay. You can see x error is simply linearly increasing. So, it is an increasing, it is an actually kind of increasing function. So, it is a parabolic, it is coming from 60, then it is coming to minimum say minus 40, again it is increasing, and x derivative obviously it is increasing throughout. So, first order fit is not a good solution for a second order signal. So, next thing we will try to do the same thing using a second order polynomial fit. So, this time I have taken a second order polynomial or it is a position, velocity and acceleration model. With this I just do the fit, you can see actual versus estimated, quite closely they are matching. And if you see the error, you can see first the x is okay within say bound is within small say 15 to 20, and you can see x dot and x double dot other things. So, they are also within the range. So, the best performance is achieved when actually your filter or your least square polynomial model is matching to your signal order. So, here just a kind of statistics I would like to give. So, signal estimation error. So, signal estimation error is actually the actually true signal minus estimate. So, when you know suppose the true. So, if it is a say filter, if it is a 0th order signal means a constant signal. Okay. So, if a constant signal you want to do a constant component, you get the least error. But suppose you are wanted to do a constant fit for a first order linearly increasing function, you get this much error, second I have not given. So, there is actually its error is infinity. Next is say now a 0th order signal, a constant signal, you wanted to do a linearly increasing position velocity function, a straight line functions, you get this much error. Do the same position function for a first order fit, okay, you get something okay good, but here second order you are totally dead. Similarly for second order also. So, the thing is that if your signal order is somehow matching to your model order, you get the bare minimum error. Now, there is a question, how will you know, because your truth will be unknown, you will be given only some measurement point, and with that measurement point you have to give some kind of fitting. So, what could be the kind of rationale behind choosing the which is the order of your model? Suppose in a tracking example, suppose you are doing a position, velocity or acceleration or something kind of estimation, you know you will be knowing that what could be my at least some approximate knowledge of your vehicle dynamics. If the vehicle dynamics is say could be of sometimes it is say constant and sometimes it could be that it is kind of constant and then changing the heading and doing something. So, in this kind of case, if you plot in that case rather than a constant velocity model, if you plot with a constant acceleration model, probably you will get a better fit. So, that is why some understanding of the truth is required. And if suppose if any kind of case when your data is very non-linear, you do not know which kind of order will be there, then simple least square may not be a good option. So, to do this there is some other techniques we will discuss later, that is called spline or any kind of statistical estimation is required. Least square is good when you actually have no prior your system dynamics little bit, some knowledge. Okay. With this actually now I would like to go through the generalized least square solution. So, as you know that as we are going order more and more, first is the constant signal 0th order, then first order position velocity, next is quadratic order position velocity acceleration, and finally is the position velocity jerk. All the 3 orders we have completed. Now, if it is an nth order system, so as you see here, it is an nth order system. Okay. With this nth order system, you have now order is n. Okay. With this order of n, now you can calculate it using your coefficient matrix or least square solution of A0 to an, all the coefficients you can actually found out using the pseudo inverse of x into your measurement vector. So, pseudo inverse of x is actually like this. So, it is a generalized pseudo inverse, all of you know about it. So, I won't talk about much about the pseudo inverse. So, this is the solution for a least square. Again I am repeating only one thing, least square solution is good when you have some prior knowledge of the system dynamics. If the measurement is too much nonlinear and you do not know, you have no knowledge of the system dynamics, least square will be difficult. Linear least square at least will be difficult. For then there are nonlinear least square, Lavenberg-Marquardt, there are other algorithms like spline fittings, piecewise linear, orthogonal linearization, all these methods are there that will be some advanced method that can be discussed later. With this, we stopped at the first basic estimation theory, because these things concepts will be important when we start tracking or when we start any classification algorithms. Okay. So, next part is I will talk the next estimation techniques. We have 2 more remaining, one is called maximum likelihood, another one is called maximum-a-posteriori. So, what is a maximum likelihood? So, say you have a measurement say is x, which is equal to your true state x plus say some random noise. Y is a say V is a kind of 0 mean wide Gaussian noise. So, what is Z? Z is my measurement report or which is coming from sensor. So, I can fairly tell that Z is my evidence. What is X? X is the underlying state that we need to find out. So, X is my hypothesis. So, my Z is my evidence. I am writing E, evidence. X is my say hypothesis, I am writing is H. V is equal to your measurement error. Okay. And it is a 0 mean wide Gaussian. So, what is the need to choose Gaussian? Gaussian means that actually you have first order statistics and second order statistics, that is enough to represent a Gaussian. So, your first order is mean is 0, second order is your variance or standard deviation, whatever you say. So, it is sufficient to characterize this thing, plus the power spectral density of any white noise is constant, that also we know. Now, we try to calculate something called likelihood function. What is called likelihood function? Likelihood function is given by this conditional probability. So, probability of evidence given the state, that means the hypothesis. So, probability of measurement given the state or in terms probability of evidence given the hypothesis is a Gaussian distribution. So, this is simply your bell shaped curve, you know, bell shaped curve. Okay. So, bell shaped curve, here is your say central point, this is your actually mean and this is your dispersion. Okay. So, this is actually your noise statistics. Okay. So, with this, so this is called your likelihood function. So, here your actually mean is kind of a 0 and here you get something called sigma. Okay. Now, I have to do the maximization of it. So, when I do maximization, so maximization of likelihood is del x of likelihood function is 0 or the log or minimization of the log likelihood, because see it is an e to the power. So, once I do it from e to the power to taking the log, I have to do it for a minimization. So, either case is same. So, if you do this, if you solve it and equate it to 0, you can get x ml is equal to your measurement point. So, that is your actually measurement Z. So, this is actually the measurement likelihood. Maximum likelihood. So, maximum likelihood is another common method of estimation. It is used in tracking, but mostly when we will talk about Kalman filter in subsequent lecture, we will be showing that how from maximum likelihood or maximum-a-posteriori, the probabilistically how the estimation is happening. We will be showing in subsequent lecture. Next, another estimate is called MAP. So, again the same system, your evidence is equal to your state plus your measurement error. Okay. So, this is your evidence, this is your hypothesis, this is your measurement error. This is your noise statistics, and this time you have a prior statistics of your x. X means your hypothesis. So, you start with the initial guess of x. Initial guess of x means you assume it is a Gaussian distribution. Gaussian means I already told you have two order statistics, first and second. First order is your mean. You assume that you have a mean value of x0 which is in error with the true value with say some root p, that is your standard deviation. Root p is standard deviation, p is your variance. So, mean of the Gaussian random variable is say x0. Okay. Now, you know Bayes rule. Bayes theorem, what it says? Bayes theorem says that probability of hypothesis given by the evidence is equal to probability. So, x is my, again I am repeating, x is my hypothesis, z is my evidence. So, probability of x given z, that means probability of hypothesis given evidence is equal to probability of z given x. This is your likelihood. So, probability of evidence given this hypothesis is likelihood into probability of x divided by probability of z. Probability of z is actually measurement report which you are actually getting from your sensor. We do not care about it. So, you can safely assume you can do it proportional. Instead of equal, you can write it proportional. So, probability of x given z is equal to proportional of two Gaussian components. One is probability of z given x, already we have done in your previous maximum likelihood when we are teaching. So, you have seen this is your one bell shaped curve, another bell shaped curve is your actually prior statistics, because I have assumed that x is also a Gaussian distribution. So, you are merging two Gaussian, one Gaussian here, another Gaussian here. Say this is your state distribution, this is your say likelihood function, two Gaussian. Now, when we merge the two Gaussian, I am getting another Gaussian is here. If you simply solve some algebra, you got another Gaussian. It is a well known property. When you merge two Gaussian, multiply two Gaussian, you get another Gaussian with a different mean and different variance. So, this x bar you get it like this, and the variance you get it like this. Now, there is a very important thing here. Very important thing, this needs to be understood, otherwise we will not be able to understand the Kalman filter. What is there here? You can see sigma is equal to root over PR divided by P plus R, or say sigma square, you then under root will go, that from standard deviation to variance if I calculate. Okay. So, this is something equal to our school days parallel resistance formula. You can now remember your replicate two parallel resistances there, you want to get your resultant resistance. So, they are kind of a parallel resistance formula. So, and we know the resultant resistance will be lesser than your individual R1 and R2. So, if your resultant resistance is R, then your should be less than when you are putting it in parallel circuit, it will be lesser than individual resistance. The same thing is here. So, your sigma is less than P and R. So, that means when you are fusing two Gaussian, the resultant Gaussian should be of lesser error. This is a very important concept. When we will teach the sensor fusion after tracking, then this concept will be very useful. This is a primarily and foundational concept of Bayesian sensor fusion, or even for Kalman filter as well, when we derive Kalman filter next. So, you have two Gaussian, one is your noise is a Gaussian, another one is your state distribution is a Gaussian. You are merging it using the Bayes rule, and you got another Gaussian whose error variance. So, that means when you merge these two, you get a very steeper curve. Okay. So, if this is your P, this is your R, and this is your say sigma. So, sigma is less than P or R. So, this is the kind of we call it the maximum a posteriori estimation. Okay. Now, we got some kind of a distribution, probability of xz. So, my maximum likelihood is my probability of zx. This is the distribution of max likelihood, ML. Okay. What is my map? Map is when you apply the Bayesian. So, x given z. So, now I have to, and we already know when I did my maximization function or my del x equal to 0 of the maximum likelihood function, I got x hat ml is equal to what? We just now prove it is actually z when we do del ml or say del lkh. I will write it like this, say del lkh divided by del x is equal to 0. Okay. And when you do map is probability of x given z. So, here also you have to do the same thing. So, del of map or del of probability of x given z by del of x to be 0. Okay. So, the same thing I have done here. So, probability of del x given z equal to 0. Once you solve it, so what is the thing? So, this is your final probability of x given z. Now, you would say take del x. What will be coming? Your e to the power, this term will come here. So, you get your actually x equal to your x bar. So, x at map you can say will be x bar. X bar means expectation of this mean. So, this is like this. So, now if you take your expectation operator, you just separate it out with the two component. Thus from z you can replace it with x plus v. So, evidence is equal to hypothesis plus noise x plus b into p by p plus r plus expectation of x 0 into this term, just a simple algebra I have done. Now, your expectation x is one thing, the x mean plus the constant term is coming out, expectation of v is 0. Okay. And this part is just totally constant. So, expectation of any operator, any constant operator is equal to c, the constant itself is coming. So, that is what I have written here. So, now expectation of x is what? Is your mean. If you go to the earlier slide, what I have said, expectation of means is your mean. So, that mean is x 0 into p plus r. So, ultimately simplify you will get x 0. So, x at map is equal to your x 0. So, this is your maximum a posteriori estimate. Okay. So, now what we have completed? We completed very basics of estimation theory, and this will be the foundation of tracking as well as some kind of classification and sensor fusion, because these three will be our fundamental objective in this course, and that is what we are working here. So, your initial maximum least square estimation, maximum likelihood estimation and maximum a posteriori estimation we have completed. Next part what we go with the kind of a Kalman filter. Okay. So, we will start now the very basics of Kalman filter, and then perhaps in the subsequent lecture we will demonstrate how the Kalman filter and everything is kind of looking like. So, with this say now I will go in a Kalman filter, you have to go in a state space equation. Okay. What is a state space equation? State space equation is called your dynamic states is like this. So, you know you must have studied your control system lecture. So, if you see this, then your state space equation will be x dot equal to ax plus bu, y equal to cx or hx, whatever you do, like this. Okay. The same thing is the discrete equivalent here. So, discrete equivalent is xk is equal to say phi I will explain in next lecture, xk plus 1, say some buk, or if you want to remove the b, then you can simply write wk, or zk is equal to c or h, if you or you can write x, c also is fine, not a problem, xk plus say some vk. So, this is the discrete kind of equivalent. So, this is actually your measure state equation and observation, state equation and observation equation. Okay. If you have studied your control system, how to get continuous equivalent to discrete equivalent, anyway when we will start the target model we will be explaining it here, but just for us this thing, there is some methods are there. One is called bilinear transformation, one is called Tustin transformation. So, different kind of transformation algorithms are there. Anyway, we will be showing the best one in our when we start the target model continuous to discrete equivalent. So, here with this method we come out the phi x k equal to phi of x k minus 1 plus w k, z equal to c of x k plus v k. You can replace the C is the observation matrix, you can use C, you can use H, does not matter, both are same. Okay. Now, a very important concept, very important concept. The concept is that when you go from continuous to discrete, here I have say this is a continuous model and this is a deterministic model. So, it is a control input is U is there. But here instead of a control input, what do you see? You have some white noise. In a process, white noise Wk is called the process noise and Vk is called the observation noise. What are the significance of it? And so, your linear system is corrupted with some additive process noise or additive measurement noise. Now, this is very important, this concept is very important. We might like to kind of tell in the subsequent classes of this what is the Wk and Vk. Okay, so with this actually now I would like to close this session. Thank you, thanks for your time.